November 27th, 1944. Fronhoven, Germany, northeast of Aachen. The M4A3E2 Sherman sat immobilized in the frozen mud, victim of an American mine that had torn through its track assembly just hours before dawn. Sergeant William Davidson and his crew had dismounted, working frantically to repair the damage when the distinctive crack of an 88mm anti-tank gun shattered the morning silence. The first round struck the glacis plate with a sound like a cathedral bell struck by a sledgehammer. Metal shrieked. The tank rocked backward. Davidson threw himself flat, certain that when he looked up, he would see his Sherman transformed into a smoking coffin, just like the dozens he had passed on the road from Normandy. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. But the Sherman sat intact. Smoke curled from a crater in the frontal armor where German steel had met American manufacturing, and American manufacturing had won. The German gunners fired again, and again, and again. By the time the 88mm gun fell silent, Davidson's Sherman had absorbed 8 direct hits from approximately 800 yards. One round had penetrated the right sponson, setting ammunition afire. The other 7 had failed to breach the armor entirely. The German anti-tank crew, positioned near the village of Lohn, had accomplished something remarkable that morning. They had proven that even Germany's most feared tank killer could be defeated, not through tactical brilliance or mechanical innovation, but through something far simpler and far more devastating to German confidence. American industry had learned to build armor that simply refused to fail. This single engagement, documented in after-action reports from the 743rd Tank Battalion, represented a psychological crisis that German tank crews had been experiencing with increasing frequency since June 1944. The mathematics of armored warfare that had favored German guns and German armor throughout the previous 2 years were being rewritten, not through revolutionary American tank design, but through industrial processes the Germans could not replicate and production volumes they could not match. The Sherman tank that absorbed those 8 88mm rounds was not a standard M4. It was a factory-modified M4A3E2, nicknamed the Jumbo by American crews. Fisher Body had welded 38mm of additional armor plate directly onto standard M4A3 hulls, bringing total frontal thickness to 101mm, exactly equal to the Tiger I that German propaganda had proclaimed invincible. But thickness alone tells only half the story. The armor plate itself, rolled homogeneous steel produced in American mills operating at scales German industry could not approach, possessed material properties that German metallurgists had sacrificed in their desperation to maintain production volumes while fighting a losing war on multiple fronts. By late 1944, German armor plate suffered from critical deficiencies in alloy composition. Nickel, molybdenum, and manganese elements that provided steel with ductility and resistance to cracking had become strategic materials. Germany could no longer obtain in necessary quantities. German tank armor from this period tested at extremely high hardness values, sometimes exceeding 400 Brinell, but this hardness came at catastrophic cost. The armor shattered rather than deformed. It spalled fragments into crew compartments even when rounds failed to penetrate. Welds split under impact stress. American armor plate for the Sherman maintained hardness values between 220 and 260. Brinell, carefully balanced between hardness and ductility. The steel absorbed impact energy by deforming rather than fracturing. Welds held under stresses that would have torn German armor assemblies apart. Field repairs could be accomplished with standard equipment by mechanics with basic training. Spring 1943. Kummersdorf Proving Ground. Brandenburg, Germany. Sherman Tank USA 306-7641. Captured in Tunisia and designated Butterpanzer 259 by its German captors, rolled off a transport rail car bearing fresh paint, German crosses, and license plate WH058941. Test engineers had already stenciled armor thickness measurements across every surface, preparing for the most comprehensive automotive examination German engineering could devise. The captured Sherman represented something that worried German tank designers more than any tactical defeat. It was physical proof that American industry had solved problems German engineers did not realize they needed to solve. The tank had been driven 350 kilometers across North African terrain by a German reconnaissance unit, a journey requiring 4.5 days. Every kilometer revealed manufacturing excellence that contradicted German assumptions about American industrial capability. The engine never overheated. The transmission never failed. The final drives maintained consistent performance. German tank crews, accustomed to frequent mechanical stops even on short movements, had watched with growing unease as this enemy vehicle simply worked without complaint through terrain and conditions that would have disabled their own equipment. At Kummersdorf, systematic testing began. Powertrain specialists disassembled the transmission and discovered herringbone-cut gears, a design standard in American automotive manufacturing since the 1930s that distributed stress across multiple teeth, simultaneously, providing exceptional durability with minimal precision requirements. German engineers had considered herringbone gears too difficult to mass-produce given their industrial capabilities and workforce training. The Americans had been manufacturing them by the thousands. The Continental R975 radial engine demonstrated remarkable tolerance for varied operating conditions. Test engineers noted that the engine maintained consistent performance across temperature ranges that would have caused German engines to overheat or lose power. The cooling system, though simple in design, proved highly effective. The air filtration system handled desert sand without the frequent clogging that plagued German tanks in North Africa. But the armor examination revealed the most significant findings. German metallurgists subjected sample plates to microscopic analysis, hardness testing, and ballistic trials. The homogeneous armor plate showed consistent material properties throughout its thickness, with no evidence of the surface hardening that German armor employed. This puzzled German engineers initially. Their own tanks used face-hardened armor with a hard surface layer designed to shatter armor-piercing caps. Further testing revealed why American engineers had chosen homogeneous steel. Against armor-piercing capped rounds, the standard ammunition by 1943 homogeneous armor actually provided superior resistance. A Sherman 75mm APC-BC round could penetrate face-hardened Panzer IV frontal armor at 940 meters, but could penetrate equivalent thickness homogeneous armor only at 150 meters. The Americans had built their tanks to resist the weapons they would actually face, not the weapons German doctrine assumed would be used. The weld quality particularly impressed German inspectors. Sherman armor plate was joined using nickel-based electrodes that produced welds with strength exceeding the base metal. These welds showed no tendency toward cracking or separation under impact stress. German tank production, desperate to maintain output volumes, had compromised weld quality through rushed procedures and inadequate electrode supplies. Field examination of knocked-out German tanks routinely found split welds as common as armor penetration as causes of catastrophic failure. The Kummersdorf report, circulated to senior Wehrmacht commanders and tank designers in mid-1943, concluded with observations that were professionally devastating. Quote, "The enemy vehicle demonstrates manufacturing sophistication that exceeds current German capabilities. Mechanical reliability is exceptional. Armor quality is superior to German production armor of comparable thickness. The implications for sustained armored operations are significant." End quote. These conclusions reached German high command just as American Sherman production was accelerating toward peaks Germany could not match. In 1943, American factories produced approximately 19,000 Sherman tanks. German factories produced approximately 6,000 tanks of all types combined. By 1944, when German tankers began encountering Shermans in France and along the Eastern Front in Soviet service, the production disparity had grown even more pronounced. The arithmetic was simple and brutally clear. A Sherman tank that reliably reached the battlefield and fought effectively was infinitely more valuable than a Panther with a superior gun that broke down before engaging the enemy. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. A tank battalion with 80% of its vehicles operational could execute missions that a battalion with 40% operational vehicles simply could not attempt. But German tankers in 1944 faced a more immediate problem than production statistics. They faced American armored formations that included a small but significant number of vehicles they had not been trained to engage. The M4A3E2 jumbo Sherman appeared on European battlefields in limited numbers beginning in July 1944. Only 254 were manufactured, assigned primarily to armored divisions requiring assault tanks for close infantry support against fortified positions. German tank gunners, trained to engage standard Shermans with confidence that their guns would penetrate at normal combat ranges, now occasionally encountered vehicles that absorbed direct hits and continued fighting. The psychological effect was devastating. A German tank commander who had successfully engaged multiple Shermans could suddenly find his armor-piercing rounds bouncing off frontal armor they should have penetrated easily. December 1944, Bitburg, Germany. Another M4A3E2, advancing with the 4th Armored Division toward Bastogne during the Battle of the Bulge, took 4 88mm hits from approximately 800 yards. 1 round bounced off the glacis plate, 2 bounced off the mantlet. The 4th struck the gun mantlet's telescope aperture, the only penetration that finally disabled the tank. The crew survived. These engagements fundamentally violated German understanding of the armored battlefield. An 88mm anti-tank gun, whether the Flak 36 on its wheeled carriage or the KRK 36 in a Tiger I turret, fired armor-piercing rounds at velocities approaching 1,000 meters per second. These projectiles generated kinetic energy sufficient to defeat any medium tank armor at ranges exceeding 2,000 meters under ideal conditions. Against a standard Sherman with 63mm of frontal armor, an 88 could achieve penetration from ranges where the Sherman gunner could not effectively return fire. German tankers who survived encounters with multiple Shermans did so by exploiting this range advantage, engaging from positions where enemy fire could not reach them. But a jumbo Sherman with 101mm of frontal armor at 47 degrees from vertical created effective thickness, approaching 150mm against projectiles striking at typical combat angles. At 800 yards, the standard engagement range for tank duels in European terrain, even the formidable 88mm gun began approaching its performance limits against this thickness. The problem was not purely metallurgical. German ammunition quality had declined alongside armor quality as the war progressed. Armor-piercing projectiles required precise heat treatment to achieve optimal hardness without brittleness. Projectiles that were too soft deformed without penetrating. Projectiles that were too hard shattered against armor face. The manufacturing tolerances were unforgiving, and German industry in 1944 no longer possessed the capacity to maintain consistent quality across production volumes. American ammunition benefited from industrial maturity accumulated across decades of commercial production requiring precisely controlled metallurgy. The projectiles maintained consistent performance characteristics. When an American 75mm or 76mm gun engaged a German tank, the crew could rely on ammunition that performed exactly as designed. German crews faced increasing uncertainty about whether their ammunition would penetrate armor it theoretically should defeat. This reliability gap extended beyond ammunition to every system that determined combat effectiveness. American tank radios worked consistently. German radios failed with increasing frequency. American optical sights maintained zero through rough handling. German sights lost calibration. American gun stabilization systems, though limited compared to later designs, provided firing advantages that German tanks completely lacked. The accumulation of small advantages multiplied into decisive operational superiority. June 6, 1944, Normandy, France. Lieutenant Francis Baker commanded a Sherman tank equipped with the improved 76mm gun, designed specifically to provide better armor penetration against German heavy tanks. On November 20, 1944, during combat against German Mark V Panther tanks, Baker engaged an enemy vehicle at approximately 800 yards range. His gunner placed the first round precisely into the Panther's side armor, a location American training manuals identified as vulnerable to the 76mm gun. Baker watched through his commander's periscope, expecting to see the characteristic flash and smoke of a successful penetration. Instead, the round bounced off the side armor without effect. His gunner fired 6 more rounds at the same target, hitting from turret to track. All 6 rounds bounced off or shattered against the Panther's armor without penetrating. The German tank commander, realizing he faced possible support from American tank destroyers equipped with 90mm guns, began withdrawing from the engagement. Baker was completely surprised to see the Panther moving after receiving 7 direct hits from his gun. The engagement was documented in after-action reports and later analyzed by Army ground forces to understand the performance gap between American expectations and battlefield reality. This combat illustrated a fundamental asymmetry. American tank crews engaging Panthers or Tigers from frontal aspects faced vehicles. Their standard ammunition could not reliably penetrate at typical combat ranges. German tank crews engaging standard Shermans faced vehicles. Their guns could penetrate with confidence from ranges where the Sherman could not effectively return fire. The mathematics favored German armor and German guns in direct confrontation. But direct tank versus tank confrontation represented only a fraction of actual combat engagements. Comprehensive analysis of tank losses in European combat revealed that the majority of Sherman casualties came not from German tanks, but from anti-tank guns, mines, infantry, anti-tank weapons, and artillery. Sherman crews spent vastly more time engaging soft targets, infantry, fortifications, supply vehicles, artillery positions, than engaging enemy armor. For these missions, the Sherman excelled. The 75mm gun fired high-explosive rounds containing 660 grams of explosive filler, compared to only 390 grams in the 76mm gun's HE round. This made the 75mm vastly more effective against bunkers, buildings, and infantry positions. Many American tank crews actually preferred the 75mm armed Shermans over the supposedly superior 76mm versions, specifically because the combat they experienced required excellent HE performance more than anti-armor capability. German tankers, by contrast, found themselves increasingly forced into defensive positions, where their theoretical advantages in gun performance and armor protection could not compensate for numerical inferiority and mechanical unreliability. A Panther battalion that began a defensive action with 40 operational tanks might have only 20 functioning after 3 days of combat, not because of battle losses, but because of mechanical failures that overwhelmed German maintenance capacity. Sherman battalions maintained operational readiness rates consistently above 75%, even during sustained combat operations. This reliability differential meant that even if individual German tanks were superior in direct combat, American formations maintained combat power, while German formations degraded through mechanical attrition faster than they could be replenished. The Battle of the Bulge, Germany's last major offensive in the West, demonstrated this dynamic with brutal clarity. German commanders committed virtually every operational tank they could assemble, including Panthers, Tigers, and King Tigers representing Germany's most advanced armor against American forces they believed were demoralized and unprepared for winter combat. The German offensive achieved initial surprise and significant territorial gains. But within days, the German spearheads began experiencing mechanical failures that overwhelmed their ability to maintain offensive momentum. Kampfgruppe Piper, the most dangerous German armored formation, abandoned dozens of vehicles, not because they were destroyed in combat, but because they had broken down, and German mechanics could not repair them quickly enough to maintain the advance. American armored formations, initially caught off guard and forced back, stabilized within days. The 4th Armored Division executed a fighting advance of 22 miles through snow, mud, and German resistance to relieve Bastogne. Sherman tanks that broke down or were damaged could be repaired quickly, using standardized parts available throughout the American logistics system. German tanks that failed mechanically were often abandoned because replacement parts were unavailable or because recovery vehicles capable of towing them had themselves broken down. The Sherman-designated Cobra King, an M4A3E2 jumbo assigned to Company C of the 37th Tank Battalion, led the column that broke through to Bastogne on December 26, 1944. The tank had been knocked out during fighting in France during November, repaired, and returned to service, a routine process in American armored operations that was becoming increasingly impossible for German units. By January 1945, German armored forces had been pushed back to their starting positions with catastrophic losses in men, vehicles, and material they could not replace. American armored formations had taken significant casualties but had been reinforced and re-equipped faster than they had been depleted. The industrial advantage that German test engineers had identified at Kummersdorf in 1943 had proven decisive. German tank crews who survived long enough to accumulate combat experience developed healthy respect for American armor, despite its technical inferiorities. A Tiger tank commander interviewed after the war was asked which tank he would prefer to fight in if given the choice. His immediate answer, Tiger. But when asked which tank was actually better at winning the war, he acknowledged the Sherman's reliability and numerical superiority made it the more effective weapon despite its disadvantages in individual combat. Soviet tankers who operated American Lend-Lease Shermans on the Eastern Front provided unique perspective on comparative tank performance. Colonel Dmitry Loza commanded a Sherman tank battalion from late 1943 through the end of the war, fighting across Ukraine, Romania, Hungary, Czechoslovakia, and Austria. He had 3 Shermans shot out from under him during this period but survived to write detailed memoirs of his experiences. Loza's assessment was nuanced. He acknowledged that the Sherman was inferior to German Panthers and Tigers in direct tank versus tank combat. The 76mm gun could not reliably penetrate Panther frontal armor even at close range. Sherman frontal armor could not withstand Panther or Tiger fire at typical combat ranges. These were simply facts of armored warfare that every Sherman crew learned to respect. But Loza emphasized that Soviet tankers did not fight on the basis of the Sherman's disadvantages. They fought on the basis of its advantages. The Sherman was mechanically reliable in ways the 34 was not. The Sherman had excellent crew ergonomics that allowed sustained operations without exhausting the crew. The Sherman had superior optics and vision devices that gave crews better situational awareness. The Sherman could be repaired quickly in field conditions. Most significantly, by late 1943, when American Shermans began reaching Soviet units, the strategic initiative had shifted decisively to the Red Army. Soviet formations no longer needed to fight desperate defensive actions where individual tank superiority might have mattered. They could maneuver, concentrate forces, and engage German armor under conditions they controlled, rather than conditions German commanders preferred. Loza described an engagement where a German Tiger tank caught his Sherman column by surprise and knocked out the lead tank, attempting to cross a road. Rather than accepting battle on the Tiger's terms, Loza used smoke pots to blind the German gunner, allowing his entire unit to cross safely, while the Tiger commander, unable to see through the smoke and uncertain what forces he faced, chose to withdraw rather than risk being surrounded. This tactical flexibility, the ability to choose when to fight and when to maneuver, was itself a product of numerical and mechanical superiority. German tank commanders by 1944 increasingly found themselves forced to accept battle under disadvantageous conditions because they lacked the operational freedom to maneuver away from threats. American and Soviet commanders could afford to avoid unfavorable engagements because they knew reinforcements were available and mechanical reliability allowed sustained operations. The armor quality difference extended beyond simple thickness measurements to fundamental differences in manufacturing philosophy. American armor plate was produced in massive rolling mills operating at scales unmatched anywhere else in the world. Bethlehem Steel in Pennsylvania, Carnegie Steel in Ohio, and U.S. Steel in Indiana collectively produced more armor plate monthly than German industry could produce in a quarter. This production volume allowed American metallurgists to maintain strict quality control. Armor plate that failed to meet specifications could be rejected without disrupting production schedules. German armor production, operating at maximum capacity while simultaneously producing structural steel for U-boats, gun shields for anti-aircraft weapons, and countless other steel products, could not afford to reject questionable material. Armor plate that would have been rejected in American mills entered production in German tanks because there was no alternative available. The welding that joined this armor into completed tank hulls revealed even more significant quality differences. American tank production employed welding electrodes specifically formulated for armor plate nickel-based electrodes containing 18% chromium and 8% nickel, with manganese or molybdenum coatings that produced welds, capable of matching or exceeding base metal strength. These welds could be applied without preheating or post-heating the armor plate, allowing rapid production without compromising weld integrity. German tank production, facing chronic shortages of nickel and specialized welding materials, increasingly relied on expedient welding procedures that produced joints vulnerable to failure under combat stress. Post-battle examination of knocked-out German tanks routinely found split welds along armor plate joints, even when the armor plates themselves remained intact. The tanks had quite literally come apart at the seams. A preserved Sherman tank located near Weibrin, Belgium, provides physical evidence of both German gun performance and American armor quality. This late-production M4 Sherman, belonging to the 84th Infantry Division, was engaged by a German Panther tank during January 1945. The tank crew had welded additional spaced armor plates in front of the driver's position field modifications that American crews applied with increasing frequency as they encountered German anti-tank weapons. The Panther's 75mm L-70 gun fired 3 rounds at the Sherman. The first round penetrated both the spaced armor and the hull armor, killing the driver instantly. A second round penetrated the front hull just below the first, entering the crew compartment. A third round struck the armor plating but bounced off, leaving a deep gouge but no penetration. The tank was knocked out but remained largely intact, testament to armor quality that prevented catastrophic failure even when penetrated. German tanker Hans Herost of the 116th Panzer Division described an engagement with a Sherman near Weibrin during the Battle of the Bulge that illustrated the tactical complexities of armored combat. His Panther had fired on a Sherman and scored a hit on what appeared to be a bogey wheel, damaging the tank's mobility but not destroying it. The Sherman returned fire, barely missing Herost's Panther. Herost expected an easy victory. His Panther mounted a gun that should have easily destroyed a Sherman at that range, but the engagement occurred at night, with a burning building providing illumination. Herost suddenly realized the light had destroyed his night vision while potentially illuminating his Panther against the darkness beyond. The American Sherman crew, positioned in darkness, retained their night vision and tactical advantage. Rather than press the attack and risk encountering a prepared ambush, the American Sherman might have had supporting tank destroyers or additional tanks positioned in the darkness. Herost ordered his Panther to withdraw. The decision reflected combat-experienced caution, but it also reflected the reality that by late 1944, German tankers could no longer assume tactical superiority even when they possessed technical advantages. American tank crews, through brutal experience, had learned how to fight effectively despite their vehicles' limitations. They used terrain to get close enough for their guns to penetrate German armor. They used infantry support to suppress German anti-tank weapons. They used numerical superiority to flank German positions, accepting losses in the knowledge that replacements were available. They exploited superior battlefield mobility and mechanical reliability to force German armor into disadvantageous positions. Most significantly, American crews understood that destroying German tanks was not their primary mission. Their mission was enabling American infantry to capture and hold ground. A Sherman that suppressed German infantry positions, destroyed machine gun nests, and eliminated anti-tank guns, while avoiding direct confrontation with German heavy tanks, was fulfilling its mission successfully, even if it never knocked out a single German tank. German doctrine, by contrast, emphasized tank versus tank combat as the decisive element of armored warfare. This emphasis drove German tank design toward vehicles optimized for killing other tanks, thick armor, powerful guns, sophisticated fire control systems. But these design choices came at the cost of mechanical reliability, ease of production, and logistical sustainability. A Tiger tank with its 88mm gun could theoretically destroy any Allied tank at ranges where it could not be harmed. But Tiger production never exceeded 25 vehicles monthly, and mechanical reliability was so poor that units equipped with Tigers spent nearly as much time repairing them as fighting with them. A tank battalion equipped with Tigers might possess fearsome combat power when all vehicles were operational, but maintaining that operational status required logistics support that German industry could not sustain. The Panther, designed to provide the combat power of a Tiger in a more producible package, suffered similar reliability problems throughout its service life. The transmission, final drives, and engine cooling system all demonstrated chronic failures that limited operational readiness. German tank units equipped with Panthers routinely reported operational readiness rates below 50%, meaning that at any given time, more than half the battalion's tanks were under repair rather than available for combat. American tank battalions equipped with Shermans maintained operational readiness consistently above 75%, even during sustained combat. Operations. This 25 percentage point difference in availability translated directly into combat power. A German armoured division with 100 Panthers assigned might field 50 operational tanks on a given day. An American armoured division with 100 Shermans assigned would field 75 or more operational tanks that same day. The mathematics of attrition warfare favoured the side that could maintain vehicles in operation. German armoured formations that began defensive battles with numerical parity found themselves outnumbered within days, as mechanical failures reduced their effective strength faster than combat losses. American armoured formations maintained their strength through sustained operations because their vehicles simply kept working. By March 1945, as Allied forces crossed the Rhine and drove into the heart of Germany, the armoured balance had shifted so decisively that German tank crews often chose to abandon their vehicles rather than fight against overwhelming American armour superiority. Panthers and Tigers were found intact by advancing American forces, abandoned because they had broken down, and German crews saw no point in dying beside vehicles they could not repair or move. The final irony was that some of the most reliable armoured vehicles in German service during the last months of the war were captured American Shermans. German recovery units gladly pressed captured Shermans into service as armoured recovery vehicles, specifically because their powertrains were so much more reliable than German equipment. A Sherman could be counted on to start, run continuously, and tow disabled German vehicles without itself breaking down capabilities. German recovery vehicles increasingly lacked. Post-war examination by American and British intelligence organizations confirmed what German testing at Kummersdorf had revealed 2 years earlier. Systematic analysis of destroyed German tanks found mechanical failures as common intrasteep, as combat damage as causes of loss. Final drives broken from stress, transmissions seized from inadequate lubrication or operator error, engines burned out from overheating or oil starvation. The German obsession with individual vehicle superiority and impressive specifications had blinded them to the critical importance of reliability and maintainability. They built tanks that no conscript mechanic could maintain without extensive specialized training, powered by engines that demanded constant expert attention from skilled technicians, supported by a logistics system that collapsed under the accumulated strain of supplying countless unique parts to scattered units. The lessons learned through testing, captured Shermans directly influenced German tank design thinking in the post-war Bundeswehr of West Germany. When the Federal Republic began developing the Leopard 1 main battle tank in the 1950s, designers consciously emphasized reliability and maintainability over pure performance specifications. They studied American automotive engineering principles and deliberately applied them to military vehicle development. The resulting Leopard 1 incorporated many design philosophies that had made the Sherman successful: robust powertrain with substantial design margins, easy maintenance requiring minimal specialized tools, standardized components, enabling rapid field repairs, growth potential allowing future upgrades without complete redesign. The Leopard 1 became one of the most successful tank designs of the Cold War era, serving with numerous armies and remaining in production for decades. The M4A3E2 Sherman that absorbed 8 88mm rounds near Fronhoven represented far more than a single vehicle surviving enemy fire. It was tangible proof that armor quality mattered more than armor thickness alone. That manufacturing excellence determined battlefield performance. That industrial maturity translated directly into combat effectiveness. Every Sherman that remained operational after German tanks had broken down was evidence that reliability mattered more than firepower specifications. Every American armored division that maintained its strength through sustained operations, while German divisions degraded from mechanical attrition, was proof that logistics and maintainability determined which side could sustain offensive. Operations. The Sherman did not win World War II through technical superiority in firepower or armor protection. It won through industrial superiority expressed as mechanical reliability, consistent availability, and ease of maintenance. German engineers at Kummersdorf understood this by mid-1943, based on their exhaustive testing. They wrote detailed reports documenting their findings. They reached correct conclusions about American advantages. But understanding a problem and solving it are fundamentally different challenges. German industry lacked the capacity to retool production around reliability principles, while simultaneously fighting a losing war on multiple fronts against enemies with superior resources. American industry had built reliability into its civilian automotive sector over decades of commercial competition and simply extended those mature principles to military production with remarkable success. The title of this video suggests German tankers refused to believe the Sherman could absorb 88mm shells at 400 yards. The historical reality is more nuanced and more devastating. German tankers believed their guns were superior because German propaganda told them their equipment was the finest in the world. German test engineers knew their guns were superior because they had data proving German armor-piercing ammunition could penetrate Sherman armor at ranges exceeding 2,000 meters. What German tankers gradually learned through bitter experience was that technical superiority meant nothing when their tanks broke down before reaching the battlefield. That armor penetration capability meant nothing when ammunition quality had deteriorated to the point that rounds shattered against armor they should have penetrated. That gun performance specifications meant nothing when mechanical unreliability prevented them from maintaining operational vehicles in sufficient numbers to contest American numerical superiority. The captured M4A3E2 jumbos that occasionally appeared on European battlefields in late 1944 forced German tank commanders to confront a new reality. American industry had not merely matched German armor quality, it had exceeded it in the metrics that actually mattered for sustained combat operations. The Sherman absorbed punishment that should have destroyed it and kept fighting. It remained operational when German tanks had failed mechanically. It appeared in numbers German production could not match, and German logistics could not support if they could somehow match production. Every German tanker who encountered a jumbo Sherman and watched his 88mm rounds bounce off frontal armor experienced the same psychological shock Sergeant Davidson's crew inflicted on that anti-tank gun, crew near Fronhoven. The realization that German technical superiority had become a myth, that American industrial capacity had proven more decisive than German engineering excellence, that the war was already lost because Germany could not match American production regardless of how superior individual German tanks might be. The mathematics were inescapable. The United States produced 49,000 Sherman tanks during World War II. Germany produced approximately 25,000 tanks of all types combined over the same period. American factories simultaneously produced this overwhelming tank force, while also manufacturing hundreds of thousands of aircraft, tens of thousands of artillery pieces, millions of small arms, and supporting Allied nations through Lend-Lease shipments. German factories struggled to maintain even their reduced production levels, while Allied strategic bombing systematically destroyed industrial capacity and transportation networks. By late 1944, German tank production was declining, even as American production continued increasing. The disparity in available armored vehicles meant that American tank units could afford casualties in ways German units simply could not. An American tank battalion that lost 20 Shermans in a week of fighting would receive 20 replacement tanks within days from depot stocks maintained throughout the theatre. A German tank battalion that lost 20 Panthers in the same period would likely receive no replacements at all because none were available. The American battalion could plan its next operation, knowing it would have full strength. The German battalion had to plan defensively, knowing its effective strength had been permanently reduced. This reality made American tactical doctrine viable despite Sherman inferiority in tank versus tank combat. American commanders could order aggressive advances knowing that mechanical reliability and replacement availability would sustain offensive operations. German commanders could only defend, knowing that every tank lost represented irreplaceable combat power and that mechanical failures would degrade their force faster than combat casualties. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.